Hello and welcome to session 250 in the AISafety.com reading group. Tonight we'll be discussing the first half of the article A Generalist Agent by Scott Reed and others. This is a work done by DeepMind. Scott Reed is the primary author, but there is a team of 21 people, and I'm not going to find all of their pictures. It's published very recently, so it's like a couple of weeks old at most. The word gato, as far as I could tell, it's not described why they chose that name. It means cat in Spanish, and it's probably not an acronym. I could at least generalists probably an agent, that's like GA, and then you could T is probably transformer and maybe optimizer or something like that. I couldn't find anything else, so I don't think it's an acronym of a word. I also don't really think it's an agent. I realize some people say everything that has to do with reinforcement learning is an agent, but I don't prefer such a limited. Like most people, when they hear talk about an agent, they don't think something like Gato, in fact. So let's start out with a few reactions to this paper. It's been very mixed. Someone like Daniel Kokotayo was willing to call this indeed subhuman level AGI, that we do in fact have AGI here. Other people like Nostalgia Bryce made some very dismissive comments saying this work is like totally what we could have expected and was really underwhelmed. But one thing that certainly was not underwhelmed was the prediction markets, because around the time when this was revealed, the prediction markets for when we would have weak AGI moved dramatically to become dramatically shorter, going from 2048. You might be able to see here in this graph, it's on a logarithmic curve here, so it looks like it didn't go that far down, but it's actually from 2042 to 2028, which is a rather dramatic shortening of timelines. I looked a bit around what people said to that, and a lot of the people said this was a crazy overreaction, and mostly because not because it changed that much, but because saying this could only happen in 2042 was already crazy. So the market is correcting in some way. I must admit, I looked more into the details of this bet in particular. And one of the things required for weak AGI is passing the Turing test. So you need to be able to follow a scenario somewhat like what Alan Turing originally envisioned. And that probably requires more than human level intelligence to do. And also, in fact, it requires winning the Loebner Prize. And that's a prize that's been defunct for the past couple of years. And people, according to Wikipedia, people scorn of this prize. And that's probably why they don't give that out any longer. So this prediction here probably also to some extent reflects the probability that it will never be won, because the Loebner Prize will not be reinstated or something like that. One neural network to rule them all. That's my quote, and not one from this paper. The paper, the introduction, 4 times in a row states that Gato does a number of things, and it uses the same neural network for all of these tasks. And it's very important for them to say that it's the same neural network. And why is that a good idea? Well, you avoid all of the handcrafting that you normally have to do when you use it for different things. And there is you don't need to determine inductive biases. You get a lot more training data if you can just have one big model, and then you can train it on literally anything. Then you get a more diverse training. And of course, it's a model that can be reused, meaning that the total amount of compute that you need to use is much less. Those are the 5 reasons given in the paper. I think things like performance out of distribution is probably a lot more interesting, and probably part of the reason why we care about AGI. And of course, the key thing that enables this is that it does in fact work. So you take in more diverse training from everywhere, and then you keep getting better results on all the tasks. This scaling hypothesis that we've seen so many times. They have a number of tasks that they do, and when they just write it out, it seemed really, really diverse. You can read here all the things it can do, both in reality and in simulations and games. I couldn't find any specific reasoning why they chose the tasks that they chose. So I think mostly they maybe they had someone who was really good at robotics and then thought, we'll do some robotic tasks or something like that. And of course, the main claim that they're making is, or one of the things they're also showing that I won't go too much into details with tonight, is that if you add more data and fine tune it, then it becomes, even with a little extra fine tuning data, dramatically more capable. They have this statement: natural language is a common grounding across otherwise incompatible embodiments. And that looks kind of nice because obviously they're using a language model to do things like control robots, and why is language a part of that? I will later argue that this might not be entirely correct. And of course, another thing that we should note, and also that makes it somewhat less of an agent, is that they in fact did not use reinforcement learning. They used supervised learning and learned from that. So they could, of course, have used reinforcement learning, and I think it's just a matter of convenience that they had some expert trajectories and then they just used those. But that is, they didn't do any kind of self-play or anything like that. Finally, in the introduction, they have this statement: we hypothesize Gato can be effectively scaled towards covering any task of interest. And that certainly looks like AGI, a claim that an explicit claim from DeepMind that this is in fact an AGI. This is kind of like an intuitive sense that I had from this paper, mostly from reading other DeepMind papers. In fact, other DeepMind papers, in my intuitive sense, are very anti-hype, trying to avoid making statements like this statement, in fact. But I can't, it's hard for me to, if someone asks me to please point out the places in other DeepMind papers that are less hype than they could be. So I can't really, and certainly a lot of other research is quite hype. So it's more like regressing to the mean. Let's talk about this Gato model and all the things that it does. The overall guiding principle is to get as much data as possible and as varied data as possible. And they put all this varied data somehow into just standard tokens, which is mostly words. And the way they do this, we'll get back to the details later, but I would call that naive. Of course, it's really pretentious of me to say this research is naive in the sense that I could not do it myself. But there doesn't seem to be any big ideas. There are a number of small ideas, and we'll get to some of the small ideas later. But it's certainly not something that seems groundbreaking. And the way they are using this model is not something that is reminiscent of reinforcement learners or anything like that, but mostly like a language model. They're just taking a language model and trying to use it as an AGI and say, hey, it works, just by coincidence, or maybe not entirely like coincidence. But it's not designed with any kind of deliberate thoughts about AGI. It's 1.2 billion parameters, and that's a very small model because they want to use it to control robots in real time. And so that means when you query the model, you need to have a very fast answer. For comparison, GPT-2 was larger than this model, than Gato, and GPT-3, of course, was more than 100 times larger. So there is both a potential for it to be scaled up, and also like when you look at how impressive it is in things like text generation and try to compare it, you need to realize that it's much smaller than GPT-3. Let's talk about tokenization. the way they encode text, it seems like every half year there is like a new standard way to do it that's just a tiny bit smarter. And now we're doing using a method that looks at 32,000 subwords and maps those to integers. And images are also like divided into patches and normalized, and they have a for Atari button presses, they make those into words in a rather interesting way, and I'll try to explain how they do that. So first, they say they do it in row major order. So if you have like 9 values, you can either, this is row major order, and this is column major order, and they're using the top one. And let's take an Atari controller. This is an Atari controller, and if you squint, you can see like there is a button up and to the left and to the left and down to the left and down, and then in the middle there is in fact a button that can be clicked or not clicked. So if you imagine that you are holding the controller stick to the left and pressing down the button at the same time, that corresponds to 0, 0, 0 and then 1, 1, 0, 0, 0, 0. So in that way they turn Atari control inputs into integers. They also need for robotics, they need things like what are movements and where is the robot's body proprioception. And the way they do that is they take some of the continuous value and use some tricks to map those into some special words. So the first from 0 to 32,000, that's text, and above 32,000 and to 33,024, that's the robotics. And that is in fact the thing that makes me think this is not quite as general as a model as you think, because this way of segregating the input into two parts makes me think that when they previously said that they're turning everything into language, then that's not entirely true, because they are using in fact different values for this part. So it feels more like there are two neural networks pushed together rather than one neural network doing both. Let's talk about the loss function, which is of course specifying the loss function is a crucial thing for determining how to train a neural network. This is in fact a picture from eliciting latent knowledge that I've chosen here. And you might remember this is a Bayesian network with statements like it is raining and the sprinkler is on and there is water on the lawn and I should get an umbrella and things like that. So you imagine there are some values here that are propagated. And let's say you want to encode this kind of knowledge. So how do you calculate the probability, let's say the joint probability that this is true, this is true, this is true, and this is true? How do you calculate that? Well, that is, you can write that as a probability of A1, A2, A3, and A4, right? And how do you calculate that? You can calculate that using the chain rule. And the chain rule looks something like this. So you have the probability that A4 is true, given that the others are true, multiplied by the probability that the preceding ones are true. And this, of course, you can, if you want to calculate this, well, then you can use the chain rule again. That's A3 given these two, multiplied by the probability of these two together, and then you end up with something like this. Okay, so this is just a motivating example of how to do it for probabilities. Let's take the logarithm of all this, because we don't like, for practical reasons, we don't like to multiply. We much prefer to take the logarithm and just add things. Okay, so what's the log of the probability from S1 to SL? Well, that's the sum of the probability S1 and then for S1 to 1, and then this index becomes 2, 3, 4, and so this is basically using the chain rule. Okay, and then using this this equation, they plug it into and get a loss function for a policy and a batch size. And if we just take the batch size here, then you can see this is in fact the statement up here, the probability that you go all the way down in this tree in the Bayesian network. And there's a masking function. This masking function ensures that there are some parts of the output that we don't actually train on. And we'll get back to later why we don't want to train on that. But this equation here is the actual loss function for training the neural network. So before I can explain the masking function, we need to look at how data is actually flattened into the input in a batch. So there's some text. It could be like I'm going to London, or whatever people have posted on the internet. There could be some robotics, proprioception, and continuous action. And there's things like images with questions and Atari games, and all this are put into some batches. You can see here, and this is fed into Gator. And now, in order to train Gator with a loss function, we need to add here. They mask some of the inputs. Like if you imagine here the Atari, then we want to train on the controls, but what we predict the screen to be isn't actually all that interesting, or not something we should train on. So we mask that out in order to get our loss function. There are some more details about the training. They choose transformers for simplicity and scalability. Scalability is certainly something that transformers are good at. I'll leave it to you to decide whether the transformer architecture is actually simple. Like it seems to me like that's not the case, but it's easy for them to implement because you don't actually have to implement that because other people have implemented it for you. So like if you want to use a transformer, then that's not very difficult, right? Because other people have done it. And some more description about the parameters for the transformers and some other details about how they do that, and they add some prompts. Always want to do demonstrations. The hardware they're using is a bit more interesting. They're using a 16x16 tensor processing unit version 3. And version 3, that's a bit strange, right? Why are they not using TPU version 4? Well, the conspirational part of me would say that, well, the TPU 4s are busy training a underlying superintelligence or something that they think they can use to take over the world. In another hypothesis, less conspiratorial, would be that this research is just old. It's something that happens quite often, that people have some kind of model and then they spend half a year and even a year before they get around to publishing it. That's certainly a thing that happens. Another thing that I think is perhaps most likely is that they simply did not care. And I'll explain why in just a moment. The time they used to train this was 4 days. So if you calculate, that's 256 TPUs running for 96 hours. That comes out to around 25,000 TPU hours. And Google will rent you these TPU hours for $2, meaning that I mean, people can probably get them a lot cheaper than, but even then we're talking about a price point of like $50,000, and for a paper with 21 authors, I think this is peanuts really. The training costs are totally trivial. They trained it for 1 million steps. I could not find the stop criteria being used, but yeah. And they have some more details about this. That's of course interesting if you want to reproduce this, but might not be interesting for us. Likewise, there's here some more description of how the deployment works in Atari games. I don't think I'll go through that. The data sets, I won't go through that in detail, but one thing you'll notice is that there are vision and language tasks, and there are control tasks. And the control tasks are in fact 85%. And there seems to be like a decent spread over different tasks. and also in the vision language, most is massive text. I thought there was, I noticed a dataset called the Align dataset, and I thought, hey, they're actually doing alignment work, and wonderful. What's the Align dataset? And it turns out to be something with image recognition, unfortunately, and that has nothing to do with alignment. So that's a bit sad that people are choosing such a misleading name. I don't think it's malice, it's probably just ignorance. The people who are working with this just are not really aware that there's something called AI alignment, and they are just choosing the name for all the reasons. Let's talk about the simulated control tasks. They have a number. There is the Atari, Sukuban, Grid World, instructions following, some physics-based simulations, first-person 3D, procedural, Atari, OpenAI Gym, Robot simulation, and meta environments. So it seems to me like quite varied as far as I can tell. They, of course, don't do self-based. Excuse me for a moment. They only do use experts playthroughs from the best reinforcement learners, and only in the cases where the agent is successful. And some, like Montezuma's Revenge, this is a non-trivial constraint. What does that do? My intuition is that on the average case, it probably makes it better, but in the worst case, because we haven't seen anything like that, the worst case could be worse. But that's kind of an intuition about the consequences of this choice. Okay, let's go from simulation to reality and stacking red, green, and blue blocks. And there are two overall tasks: skill mastery and skill generalization. Skill mastery is like how well can you stack these blocks on top of each other, and skill generalization is if you have only stacked green on blue and suddenly you want to stack blue on green, can you figure that out? They're both doing this in simulation and in fact in reality, so they do have actual robots doing this. And the episodes are running at 20 hertz, so that turns out to be requiring an end-to-end time of 50 milliseconds for querying this model. And that's a very, very substantial constraint. And that's, of course, also why they need to have such small models. And I think actually this is, as far as I can tell, a really hard constraint. And it's probably something we should be really impressed with, that they are able to make a full turnaround on this in 50 seconds. That's quite impressive as far as I can tell. And of course, it gives this very tough constraint gives a wrong picture of what this technology can do, because you could imagine that you just relax it, like GPT-3 obviously takes far longer to answer, and you also get faster computers. So this constraint is something that we shouldn't put too much weight on. And they have some examples of how Gator compares to the state of the art, and depending on how you squint, it is probably beyond the state of the art in general. This is, of course, something that people who write ML papers care really a lot about. We don't, from an AI safety point of view, it's not so important whether it's beyond the state of the art, but like the trends that this greater kind of generality, whether that is useful or not. In total, on simulated control tasks, you can see a graph here. Like there are 600 tasks, and you can see how many of them perform as well as the experts, the state of the arts, and how many of them get like 90%, and how many get 75%. This is, of course, an interesting question. The way they formulate that is, if you go up to the 50% threshold, then 75% of the tasks can be solved at the 50% threshold. And I think actually it's more interesting to see how far it's under control. Like if you go up to like 75% or something like that, well, that seems like even that's much closer to state of the art. And it's still 2/3 that you can do that for, or even if you go out to like requiring 90% of state of the art, then you can see, okay, it's still, around 50% of the tasks that can be solved at 90% of the state of the art. So I think this part of the graph is actually more interesting than the one they highlight here. Also, one thing that I think is really striking from this graph is how even the performance is, the performance curves, right? That as you increase the requirements, it very gradually falls out how many tasks follow this. It's not like there is any kind of cut-off points or anything like this. It looks like some very smooth graphs. And of course, what we've seen with scaling in general is a lot of smooth graphs, and that's also what we're seeing here. And finally, of course, what I would like to know in some of this is like, what is the human level? Because for some of these, it can be really hard to get an intuitive feel for, they just compare it with state of the art in reinforcement learning, and I would like to know, like, how are these reinforcement learners at the human level, or far above the human level, or far below the human level? Because like, if the human level is in general like 70% of the best reinforcement learners, well, then this becomes far more impressive. But if humans are generally far above the best reinforcement learners, so this is a subhuman level, well, then this becomes much less impressive. So the comparison with the state of the art, I mean, if you are a researcher in this specific field, then you have some kind of intuitive idea about what is the state of the art. Is it above the human level or below the human level? This is something that people like me have no way of knowing. I think these expert reinforcement learners are in general above the human level, but the comparison is just not made, and I'd really like to know. There are some text samples shown. It's trained on massive text and the colossal clean version of Common Call's web crawl corpus. This C4. So this is how it's trained, and it's also trained on some vision language datasets. And they show some examples, calling it rudimentary. And so, I would have liked to see some more effort in really comparing this. Like, how much better is it than GPT-2? That's a question that, like, they're not trying to answer at all. Even though obviously it's a smaller model and it's mostly trained on other things than language. I think it is in fact better than GPT-2, and that's of course an interesting thing, right? They are training it on less data, and they're training it. It's a smaller model, and it's mostly trained on other things. So it is somewhat surprising. Why does it in fact perform better than GPT-2? And I think the answer is in all these small details, like the mapping of words to integers and all these small performance optimizations that are continuously being found with the transformer architecture and way to implement this. Like, there are so many small improvements that we do in fact with a smaller model and less training data and less everything get better performance. But of course, the examples that they show, like, it's clear it's not state of the art. It's I can speculate why it's not perfect and how much the other domain help, but it's not really obvious. Finally, I'm going to talk about survivorship bias. Like, you might, some of you might have seen this picture before. This is a picture from the Second World War, where people were observing, like, counting the bullet holes on the planes that returned home, and put a red dot, and they could see, okay, there were these places that the bullets were hitting, so they thought perhaps we should up-armor those areas. And then actually they realized afterwards that no, in fact, the reason why they saw this was because those were the planes that did return home. So they should armor these places instead, because when the aircraft was hit in the cockpit, then the aircraft did not return home, in fact. And so let me try to use that as an analogy for the safety work in this paper. So Rohin Shah from DeepMind's safety team is commented on this paper, and he was asked, did he review this and what was his thought? And he did not review this, and he believed that no one at the DeepMind team did in fact review this. They would have been happy to chat with him if they had reached out, but they didn't do that. And when Rohin is reading this paper afterwards, he is looking at this and saying, this doesn't seem like something that can destroy the world. And I think you can imagine some kind of self-reinforcing bad cycle in DeepMind, where they build an AGI by people who obviously don't care the least about safety. And then they start the AGI, and the AGI does not destroy the world. And then they write a paper based on this AGI that turned out not to destroy the world. They show it to the safety team, and afterwards, and the safety team looks at this afterwards and say, oh, obviously this can't destroy the world. And they're right, because they're only seeing it after it has been published and after it has not destroyed the world. And so they update on this, saying, okay, we're seeing this, and obviously the world didn't get destroyed, so we're seeing more and more examples of the world not getting destroyed, and they become more confident. And the problem, of course, is in the cases where they build the AGI without caring about safety, then in this case, it would never reach the safety team at DeepMind. So I think there is a fundamental problem in DeepMind if they have the safety after the deployment. The safety team should be involved before the deployment. That is all I have for today. There will be much more about the paper and about safety next time.